Hello, everyone. Thanks for joining us. On behalf of the Environmental Finance Center Network, welcome to today's webinar on emerging drinking water contaminants, specifically per and polyfluoroalkyl substances, or PFAS. My name is Tess Clark. I am based here at the Syracuse University Environmental Finance Center. And before we get started with the program, I just want to go over a few points on logistics. This is the first of two webinars about PFAS that we're hosting. Today's program will cover the basics and need-to-know information, while next week's webinar will cover some interesting challenges and technological solutions. Please keep in mind that everyone will be on mute to ensure audio quality. If you have a question, just type it into the GoToWebinar question dialog box anytime throughout the session. We will be saving time for your questions at the end of the webinar. We will also be making today's slides available, as well as a video recording on the EFCN website. You can reach that website at www.efcnetwork.org. As a courtesy, we like to provide a certificate of attendance for participating in this webinar today. We do not submit our webinars to licensing agencies for pre-approval of continuing education credits. You must attend the entire 60-minute session by logging into GoToWebinar with your unique registration link in order to receive a certificate. If you watch the webinar with a friend or you're not directly logged in or registered, we won't have a record of your attendance. And lastly, I just wanted to share a little bit of information about us. This session is one of several webinars conducted by the Environmental Finance Center Network for the Smart Management for Small Water Systems project. This is a project in which we provide training and technical assistance to small public water systems in all U.S. states and territories to help local systems achieve their goals and stay in compliance with the Safe Drinking Water Act. Syracuse University Environmental Finance Center is based, of course, at Syracuse University here in New York State, and we really focus on serving communities in EPA Region 2, especially small and rural communities, in terms of capacity building and increasing community resiliency. PFAS certainly impact everyone, but we are hoping today's webinar will be especially helpful if you are in a state that has been impacted by PFAS or PFA drinking water standards. On that note, I'd like to introduce Steve LaRosa. Steve joins us from Weston and Sampson, a leading engineering and design consulting firm in the Northeast U.S. Steve has investigated many PFAS-related sites throughout New England with varied sources and levels of impact. He is an active member of the Interstate Technology and Regulatory Council PFAS Group and has presented on PFAS at numerous regional and national conferences. So on that note, I'd like to introduce Steve, and Steve, you can take it away.
Fantastic, thank you, Tess. So today's webinar is really designed to try and get folks familiar with what PFAS are, and give you some of the basic background knowledge necessary to begin addressing these in your water systems or in the consulting work that you do, if we've got any consultants with us today. So what I'm hoping to do is to go over any number of things here. Let me just make sure I'm up and running correctly. There we go. We will start with kind of a background of what PFAS are, discuss very quickly toxicology and regulatory status, move on to sampling, fate, and transport, have a very brief discussion there, and then I'd like to spend a fair amount of my time on the case studies that I have for a couple of towns in Vermont and Rhode Island. So what are PFAS? You may have heard about them in the news quite a bit recently, particularly in the Hoosick Falls, New York, and Portsmouth, New Hampshire areas. There's also a number of sites in Michigan associated with the manufacturers of these materials. They are man-made materials that are resistant to heat, water, and oil, and they have been used in hundreds to thousands of industrial applications and consumer products. They are basically a long-chain carbon molecule that is either nearly fully fluorinated or completely fluorinated. So that would mean that there are fluorine atoms at each of the bonding sites with the carbons in that carbon chain. The fluorine to carbon bond is one of the strongest bonds known to exist. So that's what gives these compounds a lot of their heat resistance and stability type of abilities out in the environment. The most common PFAS were PFOA and PFOS. They were utilized and manufactured in very large quantities up until about 2002. At that time, they were voluntarily phased out by the manufacturers in the United States. What happened at that time is alternative chemistries began to be utilized, and these essentially were shorter chain or smaller chained carbon molecules that had fluorine attached to them. And some are more complex chemistries, such as you may have heard of Gen X recently. So to discuss these compounds in a little bit more depth, and not to get too deep into the chemistry, but there are a number of general classes of per and polyfluorinated substances. There's polymer substances and non-polymer. What we'll be discussing today are the non-polymer compounds. Perfluorinated are things like the PFOA and PFOS that I mentioned before, and they are often carboxylates and sulfonates, and we'll see what that means in a minute. They're also polyfluorinated, which are not fully fluorinated compounds, and they're often looked at as precursors to the perfluorinated compounds. So they're nearly fully fluorinated. They have lots of other active groups on the end of the molecule associated with them. So if you look at the basic structure, what looks like the caterpillar on the right-hand side with the multicolored head is actually a depiction of PFOS. And that's the greens are the fluorine compounds, and the reds are oxygen, and the yellow at the end is sulfur. So these compounds have a very long carbon and fluorine tail with a small functional group head. The way these are named is very much like you saw in organic chemistry, if you took that back in college or high school. And they use buta, penta, hexa, hepta as the beginning of the name of each of these compounds, with buta being 4, penta being 5 carbon. So as you can see, there's a number of different PFAs that can be found and named just looking at adding a single carbon and a sulfur or carboxylic group to it. So what makes these compounds really function well is that they're fantastic surfactants. They like to be active on the surface of whatever they're exposed to. That could be the surface of water or even the surface of fabric. So the perfluorinated compounds are generally negatively charged, very water soluble, and are terminal. These do not break down. Even though there's a small anionic head at the end of them, they do not break down in nature. We have not found any evidence of them being able to be broken down by natural methods or by the typical oxidation methods that are used a lot in water and wastewater treatment. The polyfluorinated compounds, these precursors, however, are a bit different. They can break down by either abiotic or biotic methods and can exist as multiple different ions and often will adsorb to soils or other organic matter more tightly than the perfluorinated version of these. One of the most important aspects of the precursor compounds is that they can be transformed into the perfluorinated end products. So you can start with a molecule on the left, which has a more complicated head end. You can see there's sulfur and nitrogen, oxygen, and those things attached to it. But through these breakdown processes, you end up with a terminal compound at the end, such as PFOS. So where were these compounds used? They were used in all manner of materials and still are in their modified or newer formulations. So everything from the liners of your pizza boxes and popcorn bags to carpet, fire retardant pajamas you see there, dental floss, the firefighting foam uses a tremendous amount of fluorinated compounds. And then on the lower left is the Denver airport. And all of the fabric of those interesting looking kind of tents or spires is treated with PFOA, which is one of the primary compounds that was manufactured in the United States. There's acres and acres of that fabric out there. So again, the primary uses are firefighting foams was and still is a very large user of PFAs. Actually, the military will still only allow use of PFA or fluorinated foams in their response foams at Air Force bases and airports. The PFAs are also used in textiles. They were used in metal plating to assist with that, carpet, photography, pesticides, cleaning products. It seems like about every other week I hear of a new material that they're finding PFAs in. Now again, the PFOA and PFOS, those are octanoic acid and sulfonate, the 8-chain carbon compounds. They've been phased out in the United States, but they are still utilized in other parts of the world. Where would you find these compounds and find them being used? Obviously, airports, Air Force bases, naval facilities, firefighting, any manufacturing facilities that might be doing things like coating wire or fabric. And you find these a lot in wastewater treatment facilities and landfill leachate. The reason is not that wastewater treatment facilities or landfills use PFAs, but they end up receiving them. Wastewater treatment plants will get it in their discharge waters from industry and frankly from the discharge from humans, as we all have these compounds in our bodies right now because these were so ubiquitously used throughout our world. We've all been exposed to carpets and cleaning soaps and surfactants that have used these. And then in landfills, obviously, if you get waste materials from a manufacturer or even demolition debris that has carpet or all of the wax, paper, and treated coffee cups. And you can imagine anything that has a grease-proof paper or is a waterproof product that ends up in the landfill, they get lots of these compounds there. So the source types, AFFF, which is that firefighting foam, as we mentioned earlier, has a complex mixture of these PFAs. It also has some hydrocarbons and other compounds that are mixed with it that get released onto a fire to fight it. Manufacturing sources typically have a single or a couple of PFAs that are utilized to make whatever product they're making, although they may have a complex mixture of these depending on how their process works. Landfill leachate is very complex, as everything that's used out in society ends up in the landfill. And for wastewater treatment plants, again, it may be humans, industries, it could be surface water that's infiltrating into these plants that is also contaminated. So the release types from these sources, They're the fairly obvious type that you've seen whenever any hazardous material gets into the environment. There may be airborne emissions from a facility, the firefighting training. Very seldom do they gather all of their waters back up and treat it. So it may just be discharged to the local stream or sewer. Firefighting responses, obviously the most important thing is to respond to the fire. And if you can do some cleanup later, then that's great. Spills, again, landfill and wastewater treatment. Some non-traditional releases and redistribution methods of these terminal compounds, these perfluorinated compounds that won't break down, are application of wastewater treatment plant sludges, sometimes on-site septic disposal fields, and we know of at least 2 cases where they were irrigating golf courses with wells that were near where an airport is. And they actually drew these compounds into that irrigation water by pumping it. So release mechanisms, again, use and release of PFAS can result to impacts to air via transport from the stacks, surface soils, as that material is deposited from the air onto the surface soils, it will become contaminated. The PFAS will absorb slightly to those organic compounds in the surface soil and move along with any runoff that you have of those soils. Surface waters can be impacted by wastewater treatment facilities and runoff from soils. Groundwater by infiltration of contaminated surface water, by wastewater disposal for small on-site wastewater systems. Sediment is contaminated by either direct discharge, runoff from soils, groundwater discharge, and then the biota. So the things that are living on the soils, living in the water, will also be impacted. So we know that these compounds are ubiquitous and still utilized quite a bit in our society. We know that they can travel through and get into all sorts of things that we're potentially exposed to: surface water, groundwater and drinking water, and soils and sediments. So what is the toxicology and what are the regulatory status out there? The toxicology of PFAS is not very ironclad. Most of the studies have been done on only 1 or 2 of the PFAS that are known to have been utilized a lot. There's more study going right now, but it's not as well known as a lot of other contaminants we have out there. They have found out that PFOA is likely to be a carcinogen in humans for pancreatic, liver, and kidney cancers. PFOS is also at high levels that have been shown to be associated with cancers. And there's also potential for development and reproductive impacts. One of the most concerning factors with regard to toxicology for PFAS is that they do bioaccumulate. So they will accumulate in our bloodstream. They accumulate in the bloodstream of any of the animals and in some of the plant tissues that have been exposed to these. So health effects in humans: fetal growth, adult and child adiposity. Adiposity is what my wife now calls my spare tire that I have around my waist. It is not strictly obesity, but a tendency to carry more weight than you should. And again, we have potential carcinogens. Other health effects that have been observed while they've been doing testing of these compounds is reduced bone growth, testicular and kidney cancers, liver effects, immunity effects, and accelerated puberty. So obviously the impacts and potential health effects of these compounds can be very, very serious. So the EPA, a couple of years ago, came up with a lifetime health advisory for drinking water. And that is 70 nanograms per liter of total PFOA and PFOS. nanograms per liter is parts per trillion for those folks who don't work with these numbers every day. So it is almost 100 times lower than the concentration allowed for, say, benzene to be in your drinking water. I won't bore you with how they do the calculation for all these things, but one of the important things to note is the bottom bullet on this slide, which is that they assume that only 20% of your exposure to PFAS comes from drinking water. So we are exposed to, of the total milligrams of PFOA and PFOS that we can see per day, 80% of that comes from things other than drinking water. And that's often the dust and other things that are in our environment that we get exposed to. The good news is exposure to PFOA and PFOS should be decreasing. Their usage was phased out in 2002. The AFFF that's been used is slowly decreasing, and the concentrations of these compounds seen in folks' blood is beginning to decrease. So one of the things that I hear about a lot, particularly from water supplies, is that they were involved in the unregulated contaminant monitoring rule monitoring back in 2014. The UCMR3 looked for PFAS in large drinking water supplies, so folks who serve 10,000 users or more. And what they found was that there was really only a couple of percent of these water systems that actually showed PFAS at or above the monitoring rule, the reporting limit for the method. And as you can see on the right-hand side here, they look for 6 PFAS with PFOS and PFOA at the very top of the list. But you'll notice that the detection limits for these were 40 and 20 parts per trillion. So a total of 60 parts per trillion. So many of the folks who were monitored said, hey, we've got concentrations that are below the reporting limit. We should be in great shape. And we don't have to worry into the future. Unfortunately, what we're going to see next is that although the folks on this slide are the only ones that showed detections in the different yellow and red colors, what's happened since 2014 is that the standards that the states have been utilizing are actually getting significantly lower than what the detection limits were when this initial sampling occurred. So you can see that the EPA has a 70 part per trillion PFAS-PFOA level, but the various states have been showing much, much less. And that's because we're beginning to see more and more toxicology data that indicates that the exposure level should probably be lower than what the EPA has set up for a guideline. So as you can see, Connecticut and Vermont use a sum of 5 PFAS. Connecticut uses 70 nanograms per liter, while Vermont uses 20. New Hampshire last week came out with individual standards for 4 PFAS that if you total PFAS and PFOA, it's 27 for a total. New York, which my understanding is a number of you folks are calling in from, has recommended that the standard for PFAS and PFOA total be 10 nanograms per liter. That would be the lowest that I have heard in the nation. So many of these areas that thought that they did not have PFAS to deal with may very well have them associated with their water systems. So as a result of PFAS being identified in several communities in New York, Hoosick Falls being one that has a number of private and public water supplies impacted, the New York State Department of Environmental Conservation has been fairly aggressive at addressing PFAS. And they have a PFAS website that's, if you just type in New York DEC PFAS, you'll come right up to, that has some fantastic information in it. They have a rapid response team that has been formed so that water supplies that find PFAS in their water can contact the rapid response team, and they can assist you in how best to respond to finding these materials in your well. And to help determine whether you may be at risk, they've also done a PFOA, PFOS facility identification survey. And they surveyed, I believe, nearly all of the manufacturers and commercial businesses that had the potential to be utilizing these waterproofing and chemical proofing materials in their activities, and had them report if they still use them and how much they may have used, so you can actually look through that database and see if any of those folks are in your community or near your water supply. To get a sense of how much of an impact these compounds can have on an area, Cape Fear in North Carolina is a surface water water supply that serves hundreds of thousands of users. And they found that they had PFAS in the Cape Fear River, which is where they withdraw their water. They had one manufacturer that was upstream, Chemours, who actually produces PFAS and makes things with PFAS in it. And they were able to stop Chemours from discharging into the river. However, the concentrations of PFAS in the river remained at approximately 100 parts per trillion. So well over the EPA's guidance and well over a lot of the state's water quality standards. The state of North Carolina, in response to finding these PFAS in the Cape Fear watershed, has put together a proposal to add $6 million to their Department of Environmental Quality and 37 dedicated positions to help address PFAS that have been found in 25 public water systems around that Cape Fear basin. Cape Fear themselves have actually committed to putting in a $46 million water treatment plant to reduce the PFAS. So even at just as small a concentration as 100 parts per trillion, we're talking about $50 to $60 million worth of investment being made to try and provide folks clean water. So new and changing toxicology and frankly improving laboratory analytics are driving down the concentrations that are being seen as acceptable, and confusion abounds. As you saw on that table, the EPA and individual states all have differing compounds and differing concentrations that they're dealing with. With regard to sampling for PFAS, there is only one EPA method. It is 537.1, and it has a very specific and singular type of equipment to be able to identify these compounds. So you need to find a laboratory that does this work and knows exactly what the state-of-the-art method is for analyzing for these compounds. There is no EPA-certified method for sampling any other media, surface water, groundwater, any of those things. A modified method is being utilized that varies somewhat from lab to lab. So sampling concerns are high with these compounds. Obviously, Teflon tubing is a no-no. PTFE is a perfluorinated material. So lots of the things that we typically would use to sample a water supply for water quality can't be utilized. The detection levels are so low that having some of these materials in the air coming off of dust or as vapors from your deodorant or cosmetics might cause a false positive reading in your sample. So having the knowledge of how to sample and what you can and cannot use is very important to avoid getting a false positive reading. So again, we're talking about concentrations here for drinking water standards that are very, very low. False positives can occur and really add to the complexity of trying to evaluate what your real exposure may be. Just to get a sense of what 70 parts per trillion is, that would be one person in 2 world populations. So we're talking about an extremely low number of molecules that are even in your sample that you collect. PFAS are everywhere. They're found in the blood serum of polar bears, in wastewater, in the Pacific Ocean, where these materials were never utilized directly. And anytime you do sampling, you want to make sure you take plenty of blanks and use a laboratory that's well proven. So these compounds, from an idea of, geez, I've got these in my water supply, or maybe they were discharged somewhere nearby. They are mobile in groundwater. They do move through soils fairly readily. They're resistant to degradation, so they've been coined forever chemicals. If you find these in a sample, it's likely that you have enough of these materials around in the general area to have positive readings for the foreseeable future, unless you can remove that source. So wastewater treatment plants, I put a couple of special slides in here regarding wastewater treatment plants, specifically because they do some very interesting things to PFAS, and anyone who has a surface water intake will really want to understand what's happening in wastewater treatment facilities if they exist up gradient of their intake. So, as I said, precursors are degraded in the wastewater treatment plant and by biologic activities. So most treatment plants are aerobic or oxygen-rich by design and have lots and lots of bacteria that do a lot of degradation of compounds. This fairly complicated table shows the 5 PFAS that many states are using to regulate their water supplies. And we have 4 different wastewater treatment plants here. The thing to notice is that the influent concentrations are lower than the effluent concentrations in these wastewater treatment plants that are in the first 3 columns. The last wastewater treatment plant shows lower concentrations in the effluent than in the influent. What is happening as PFAS flow through these treatment plants is the precursors are being oxidized and degraded into the perfluorinated end compounds. So these terminal compounds are essentially being made from the precursors that are entering these wastewater treatment plants. So if we look at this graphically, you can see on the left, we have the sum of the 5 PFAS, and it's less than 20 parts per trillion. However, in the effluent, we have concentrations up around 130 parts per trillion going into the receiving waters. So if you're a water system down gradient of this wastewater treatment facility, you very well may be at risk of seeing these perfluorinated compounds, even though what's entering the wastewater treatment system is below the standards. So a couple of case studies for you that I'd like to run through just for you to get a sense of how impactful these compounds can be for 2 different release mechanisms. And then if you're signed up for the treatment system seminar, webinar that's going on next week, Kyle Hay from my office will discuss how do you treat these compounds in your water system if you see them. These case studies here that I'll be presenting again are primarily about how these materials get out into the environment and how they can spread and how ubiquitous they can be. So Bennington, Vermont is a site in the southwest corner of Bennington, very close to the Hoosick Falls, New York problem that you may have read about in the news. This plant put PFOA and Teflon on the fabrics that you saw for the Denver, Colorado airport. They did miles and miles of that fabric at this plant. After learning that the Hoosick Falls ChemFab plant had caused substantial amounts of contamination, the Vermont Department of Environmental Conservation had some private water supplies around the ChemFab plant in Bennington sampled. Those samples came back positive for PFOA ranging from 41 to over 2,000 parts per trillion. The ChemFab plant operated from the 1960s to somewhere around 2000, and it should not say 2012, but around 2002. In 2012, they actually removed the machinery from this building. So with that data from the 4 residences that live nearby this plant that you see on the lower right, there was an immediate response by the state of Vermont, who put together a local response center for folks to come and ask questions. They collected their information, their water supply information, and collected water quality samples from all of the residents within approximately 1 mile of that plant. They also immediately provided spring water to anyone within 1 mile of that plant to utilize if they wanted to do that. So this sampling occurred pretty rapid fire every day for approximately 3 months. And the map on the right has one large circle on it, and in the center of that circle where the square is actually where the plant was that you saw in the picture before. The red and orange dots that you see on the map are private drinking water supplies that are impacted by PFOA above the drinking water standard of 20 parts per trillion in Vermont. The green and blue dots are private water supplies that were sampled that were at or below the drinking water standard. What we found was that there were basically 3 areas of concern around the ChemFab plant that I showed, a previous ChemFab plant that was in the area, and a landfill. As we collected more and more data, we realized that all of these areas were actually connected together. The area of impact that you see here, where the yellow dots go from left to right and up and down, is approximately 5 miles wide by 5 miles tall. The release mechanism here was the factory stack, which emitted PFOA-laden steam and particulate that then flowed across the whole area, deposited on the ground, and migrated to the bedrock in these wells. One of the things we utilized while responding at this site was a web-based sign-up form for residents and an iPad-based data collection methodology to make sure that we could track all of our samples here. All told, more than 550 private water supplies were sampled. 270 of those, about half, were above the drinking water standard. 80 were between the detection limit of 2 parts per trillion and the drinking water standard, and approximately 200 were below the detection limit. They have been resampling all of the private wells that were initially less than 20 parts per trillion at this site. Every time that that's happened, and that's been 5 times in the last 2 years, about 10% of the wells that were below the 20 ppt level are now above the 20 ppt level. So these compounds continue to move through this area. This is a kind of a three-dimensional view of the area of impact. Way off in the distance, there's a little orange spot that's the primary plant for ChemFab. The yellow oblong to the right is the landfill, and the original ChemFab plant is the orange square that's in the middle of this map. Here is a hard to understand map, I admit, but this basically shows where the deposition of air and off gases from the manufacturing plant would have landed and been at concentrations that could potentially cause exposure to drinking water wells. That air discharge area is defined by the red line shown on this map. As you can see, nearly all of the highly impacted wells are within that air shed that's been predicted. So, in summary, there are multiple sources for PFOA at this Bennington site. The ChemFab process seems to be the primary method for exposing the community to these materials. Additional transport mechanisms include the fact that the wastewater treatment plant sludge was spread on all the farmers' fields in this area and may have basically brought PFOA to areas that may not have been contaminated by the air discharge. And again, the last use of PFOA here was over 14 years ago, yet we still see the impacts in the drinking water and soils. My final case study is one for Burrillville, Rhode Island, a very small town up in the northwest quadrant of that state. In Burrillville, they had their water system sampled by the state of Rhode Island because there are a number of old manufacturing plants nearby. And these manufacturing plants had some fireproof fabric that they worked on. There was also a mill that recycled plastics that may have utilized PFAS. When they sampled, they found that the concentration in the Oakland Association well in Burrill that serves a portion of Burrillville was impacted at greater than 100 parts per trillion. Immediately, the Rhode Island Department of Environmental Management provided spring water to everyone served by the public water supply, and also initiated sampling of the water supply wells within a quarter-mile radius of the Oakland Association well. They had several public meetings, just like Vermont, to try and inform everyone of what was happening, and they immediately began looking at the feasibility of extending a different public water supply that had tested clean from a nearby area. In order to try and define where the PFAS were coming from to get to the Oakland Association well, they needed to perform a source assessment. As I said, there were many potential sources surrounding this area. So basically, we performed a phase 1 environmental site assessment, which is to look at all of the potential sources, map them out, and make sure that we had identified all the potential areas that were impacted. We sampled all of the private drinking water supplies in the area and plotted that data on maps. And then we were able to begin targeting where we would investigate to try and determine what the source of these PFAS were. This map shows the well in the middle right portion of this aerial photograph. It's in light purple. And then all of the yellow squares that you see are uses that are associated with the historic use of PFAS. These included machine shops, the former fabric and metal plating plant. The wastewater treatment facility is located upstream of the Oakland well, and immediately adjacent to it is a small volunteer fire department. So this map shows the results from private drinking water well samples surrounding the public well. The public well is actually one of the red dots on the lower right portion of this map. And then you can see that the red dots, which are greater than 70 parts per trillion, progress up to the northwest and west. So we began our testing in the locations that are shown here in the purple, yellow, and blue. And these are soil, groundwater, and monitoring wells that we installed and analyzed. And we found a couple of interesting things here. One was that the bedrock beneath this site had a high point immediately underneath the volunteer fire department. Now, this fire department is fairly new. It's only a few years old, and they were adamant that they did no firefighting training at this facility. They did it remotely in an area quite far away from where this facility is. So we were curious, because we saw that those contaminant concentrations in those red dots went beyond the fire department and kind of uphill of the site. When we looked at the PFAS concentrations in shallow groundwater, we saw that the highest concentrations were immediately adjacent to the fire department. What we determined as we went through, and I'll go back just a couple slides here, what we determined is we looked at the contour of the bedrock and where our concentrations in the bedrock wells and in the shallow groundwater above the wells were, is that we had a complex mixture of PFAS, and we saw that the concentrations were higher in the shallow groundwater. As we looked more and more into the fire department's construction, it was revealed that their stormwater system injects water off the parking lots and floor drains immediately above the bedrock high that you saw in the contour maps. Essentially, what was happening is they were discharging waters to an area where it could directly enter the bedrock during dry periods of the year. As we looked through their facility, we found that they had a number of containers of firefighting foam that they used off-site, but they cleaned the equipment on-site. So it appears that cleaning their equipment on-site resulted in wash-down waters getting into the infiltration gallery and thereby getting into the bedrock and contaminating the bedrock wells. So I'd like to close with some important websites. The ITRC, the Interstate Technology Regulatory Council, is a fantastic resource for anything you want to talk about with regard to PFAS, how they were used, what their history is, how to test for them. They have some fantastic fact sheets. The EPA obviously is a great resource, and Northeastern University actually has a link to a map that shows all of the areas that have identified PFAS throughout the nation, so that you could take a look at your particular area to see if you've seen these in your area. So in closing, what I'd just like to hope that you walk away with is that PFAS are a very stubborn compound out there that, if present at very low concentrations, can have health impacts and are therefore a serious concern for any water supply. In addition, their ability to move through the environment and not be broken down, to be these, quote, forever chemicals, makes them something that is very difficult to track and treat and truly know that you have identified the source of where these are. Again, next week, I hope you tune in to hear Kyle Hay talk about how these compounds can be removed from drinking water supplies so that you can provide safe water to folks. And with that, I'll conclude and we can take any questions.
Great. We definitely have a couple questions queued up for you, Steve. So I'll get right into it if that's okay with you. So the first question is about septic tanks. Can septic tanks become a large source for PFA getting into the environment? And do you have any details about what the impacts of septic tanks might be?
You bet. Septic tanks can be a significant source of PFAS. We have sampled a number of septic tanks throughout that Bennington area that I gave the case study on, and they have some of the highest concentrations of PFAS that we've seen. We've also identified PFAS in the waters that are coming out of those septic tanks, because again, the septic tank and the bacteria there don't degrade these perfluorinated compounds. So yes, they can definitely be a source. The organic matter in septic tanks and at wastewater treatment facilities actually can also act as a sink for PFAS because of their high organic content. So when you pump that septic tank, where those sludges goes is very important to track, because you will be bringing PFAS to the facility that you dispose of those sludges.
Great, thank you. And so the next question is a little bit technical, but do you think you could explain what a lifetime health advisory means? We know that it is 70 ng per L, but can you maybe describe a little bit about what that means practically?
Sure. The way that they calculate that is they assume that you would be drinking water with that level of PFAS in it for 70 years, and that your body weight is approximately 170 pounds, that you drink, I believe it's 4 liters of water a day, every day for those 70 years. So there's a whole kind of virtual human being that they're using to determine what that concentration is that's acceptable for you to take in. So they make some assumptions about weight and how quickly your body can process and excrete the PFAS and those things. So it's an assumption that you're drinking a fair amount of water that's got these materials in it every single day for your whole life.
Great. Okay, that's very helpful. And so this question, I am not quite sure what the implication is, but this question is about how the concentrations are reduced in the environment without treatment. So the question is, how much time would reduce PFA concentration in water, and is it possible to wait it out? So that that's a great question, and it gets to the fact that these compounds don't degrade. What you're waiting for is dilution, essentially, so that these compounds are adsorbed to soil particles and diluted with clean rainwater and diluted as it gets into rivers. You can try and wait it out, but the analogy that I utilize is from a book I used to read to my son called The Cat in the Hat. And the way that story worked was the cat took a bath in the bathtub and he left a pink ring. And the PFAS are this pink ring. And the cat
cleans up the ring with mom's dress, and then the whole dress is pink. Then he shakes out the dress to get the stain off of that, and then the carpets are pink. And by the end of the book, the whole house and all the snow outside is light pink because he spread this one concentrated stain over everything. That's essentially what's happening with PFAS. They're seen everywhere throughout the world. And these terminal compounds, these 8-chain, 9-chain perfluorinated compounds do not naturally degrade. They're just being diluted. So could you wait it out? You might be able to wait it out until it's less concentrated, but as best as we can tell at this point, they will always be here.
That's a great analogy. It really puts it in perspective. Thanks, Steve.
Sure.
And I think we have time for at least one or two more questions. So this question is, the question asker noticed a peristaltic pump in one of the photos and is wondering what kind of tubing could you use to prevent cross-contamination if you are taking a drinking water sample?
Sure. We use HDPE, or a high-density plastic, and silicone tubing in the peristaltic pump. But all of the sample bottles that are utilized are high-density plastic. You can utilize high-density plastic tubing. There are some folks I know that use low-density plastic tubing, but I've also seen where sometimes that tubing may actually adsorb some of the PFAS, so it might reduce the concentration that you see. Regardless of what you use to sample, I strongly recommend that you take lots of equipment blanks, so you run water that the laboratory provides to you that's certified clean. You run that water through your sampling train and into a sample bottle to see if there's any leaching of PFAS into your water. There is a lab out there that has done some leaching tests on everything from the Write in the Rain paper to different types of tubing and those things. And anecdotally, they indicate to me that sometimes it's batch by batch, whether you get positive readings or not from some of these materials. So our operating procedure is to always do equipment blanks, regardless of whether we've done them before on this pump or not.
Wonderful. So we have time for, I think, exactly one more question. I do want to address, we are getting questions about how people can rewatch the webinar and how you can view the materials. We will be posting all of that information on our website, www.efcnetwork.org, and it will be available within the next few days. You can watch the recording and you can look at a PDF of the slides. We will also let you know when that's available. We'll send the same, we'll send an email to the same email that you use to register that will tell you and give you the link for where you can find those materials. Okay, and one last question, Steve. This is kind of a hard one. This question is, what is the elevator pitch that professionals in the industry should give to the general public when we're asked about PFAS? How concerned should they and us be?
That is a tough one. I think the elevator pitch is twofold. One is the drinking water impacts that you hear about on the news and all are only part of the story. We all have these compounds in us, and we're exposed to these compounds not only by drinking water, but by lots of other things in our environment. The best thing we can do is make sure that the drinking water we have is being treated and clean, and to keep pounding the drum that these types of compounds get reduced in our use from day to day.
That's a great way to end this webinar and conclude the fantastic program. Thank you so much, Steve. One last pitch to please tune in for the webinar next week. We did get a couple questions about treatment that we just didn't have time to answer on air today, and we will have a whole webinar devoted to solutions and technology next week that Steve already mentioned. So with that, Steve, do you have any closing comments?
I think I'm all set. Those are some great questions.
Awesome. Thanks, everyone, and hopefully we'll talk to you again next week.